So we'll start off with a really, really innovative idea. Affordable EEG-controlled wheelchair attachment for fully immobilized individuals. Collaborators on this fantastic project are Raahi, Jogani, Aarish, Bhojani, Sofia Sethuraman, Nadia Zaid, Marwat, Abdullah, Hasani, Hisham, Ahmad, Raed, Sharib, Isha, Agrawal, Sheza, Asif, and Vihan, Yerubandi. And so presentation.
Hello? Okay. Okay. We are the Brain Machine Interface Research Team at DiscoverSTEM located in Dallas, Texas. And could you guys please raise your hands if you have ever met someone who is fully paralyzed? Okay. Keep your hand raised if that person is able to get around on their own. There are 10 million fully paralyzed people in the world, none of whom can get around without assisted care.
132 million people are wheelchair users? What? Oh. There are 132 million wheelchair users, 8 of whom are paralyzed. This causes them to be dependent on other people and causes their morale to go down with a lack of autonomy. The goal for this project is to create a wheelchair that uses BCI that allows people that are not able to use a standard joystick to move a wheelchair. They can use their mind to control this wheelchair, causing them to be less dependent on other people, and their morale will go up consequently.
We did a lot of existing research, and we realized that the problem was that these wheelchairs become very expensive. So we started this project by turning a light on and off, and then we took a toy car, and then we made it go back and forth, and now we finally made the BCI wheelchair. Raahi will explain.
Hello. So to actually get the data, we use something called electroencephalography, or EEG. EEG is great because it allows us to capture brain signals non-invasively. So we capture the potentials between the axons. And then we combine that with a microcontroller, which is a very cheap little computer that we can use to control our hardware, and a servo motor, which just allows us to control the joystick. And so then to actually get the data out of the brain, we use something called a P300 paradigm. So what you'll see here is that there's 4 selections. So for example, forwards, backwards, right, left, right? And so when we flash one of the selections, and when I say flash, it means that we replace it with the image of a face temporarily. Human brains are very stimulated by seeing human faces. So when you look at that face, it's going to cause a peak in your brain signals, in your EEG pattern. So you can see on the graph, about 300 milliseconds after the stimulation, there's a positive peak. So we can use the EEG headset to pick up on that. And so when we flash a stimulation and we observe that peak, we know that the user has looked at this selection. If we flash the selection and there's no corresponding peak, then they're not looking at that selection. So based on this, we can figure out where the person is looking and where they want to move accordingly. So putting all that together, here's a result. This is a demo. So we have one of our other teammates who couldn't make it here tonight. His name is Vihan. So you can see he selected forward, and so the wheelchair moves forward accordingly. I think he selects forward again. There we go. You can see there was a slight issue which we'll have to address where it was about to crash into a wall. But now he selects backwards and it goes backwards. So one issue which you'll see here is that it takes a little bit of time to actually make the selection, and we can only move in increments. So how can we fix this? Right now we're working on something called SSVP, or Steady State Visually Evoked Potentials. The way that these work is that your selections are all going to be flashing simultaneously, but at different frequencies. So you can see here we have 15 hertz, 10 hertz, 30 hertz, 45 hertz. And so each of these objects are going to be flashing. And when the user looks at one of them, for in this case the 15 hertz frequency, in the EEG data, we capture that there's a combination of all these different frequencies from 1, the selection that they're looking at, and 2, all the other stuff that's going on in your brain. And so then using a technique like a Fourier transform in this example, we can turn that time domain data into frequency domain data, as shown in the graph on the bottom right. And we can see which frequencies occur at which amplitude. So in this particular case, we show that 15 hertz has a particularly high amplitude. And so we know that the user is looking at the 15 hertz selection, and we can act accordingly. So next, Aarish is going to go over our future design.
Hi. So basically, obviously what we have currently is not our completed design, it's just a prototype. This is what we would like to do in the future. So as y'all can see, there's a map down there, and that is basically a map of a residential setting. We would like to add a LiDAR sensor, and a LiDAR sensor is something that can basically sense what is coming towards the wheelchair. It basically gives the wheelchair eyes. And so we'd like to implement a LiDAR sensor in which we could upload a map of a residential or commercial setting, and that would allow the wheelchair to come up with the most effective path to take, just going from maybe the bedroom to the kitchen to the bathroom. And obviously this would show up on the screen, which we have pictured over there. And so instead of, as y'all saw in the slide before, the screen showed either forwards or backwards, this screen instead would show either living room or bathroom or backyard or something else. And so using the LiDAR sensor, the wheelchair would navigate the correct path to go there. Also, you can see the joystick. We would also like to implement a contraption on top of the joystick to allow for omnidirectional movement. Currently, we just have forwards and backwards. And so we'd like to allow for left, right, and omnidirectional movement. And as you can also see here, the implication of this project, of this innovation, is allowing 10 million paralyzed people to move around on their own without the help of a caretaker. And that's a really serious concern that we are addressing with this innovation. And so as you can see there, that is kind of where this technology was 10 years ago. There was a lot of wires, a lot of machinery, a lot of contraptions going around there. And what we have done is we've basically made an inexpensive attachment to be attached to any normal powered wheelchair, as you can see over there. And so that's our attachment on the top left. And obviously, like I told you, it's a very inexpensive prototype currently. As you can see, we're using duct tape over there. And as everybody knows here, Stephen Hawking, he was fully paralyzed, and the way that he got around was by flexing or not flexing his cheek muscles. And that's a binary response, and he said himself in interviews that it was a learning curve to understand how to move in this way. And so using our technology, he'd be moving around much easier, and his quality of life would drastically improve. These are our references, and thank you very much.
Fantastic project, and it'll be really interesting to watch how you evolve with this and potential other applications of similar technology. Fantastic job.